Okay, in this example, we have a flooring system. We have the main girders and the secondary joists spanning between these main girders. We have this floor and we assign our dead and live load value. And generally, we tend to define the section as an I-beam. If you want to use a built-up section, we go add new property and we choose the I steel and we define all the parameters, the dimensions, and the material. So we can add these dimensions from here. However, some engineers tend to use the general section, especially if they are using a non-standard section. They are adding like web plates. So they go and they use the section designer, or we can call it the general section, and we add our member here and we define these geometrical dimensions and the material as you can see here. Now we want to compare the results for the two definition of the section. Here we have a standard I-beam. We define it using the I section, the defined I section here, and the other one we have the general section. So let's go and see the definition of these two sections. We have an I-beam, a huge girder. It's 1000 millimeter depth with 400 by 25 millimeter flanges. And we define the same section using the section designer and the same material. We have the same span and the same loads. We run our model. And if we want to check the load, for example, for the dead load, we want to check the moment. We can see that the moment is identical for these two girders. So now we will design these two members. Now for this example, we will assume that the lateral torsional buckling unbraced length is the full length of the member. So we go to the overrides and we define the LTB as 1. And you will see now why we are using the assumption that the secondary beams are not bracing the main girders. However, generally in floor, especially if we have a composite concrete slab, the secondary beams will brace the main girder, especially if it's simply supported girder. However, here we want to show the differences, especially if we have a case where the lateral torsional buckling is the full length of the member or we don't have braces against LTB. So let's see. Now we have LTB is 1, the third number. The first two numbers are automatically calculated by the software. So now we will run. We see that we have differences in the results. Let's first see the ratio. Now we have one member. It has 0.926, the demand over capacity ratio, and the other member is 2.376. It's failing by a big margin. So what's the problem here and what's happening? Now, if we go to the section, the normal section we are using, and let us see the results. We will see that the moment acting at this section is 3,447 kilonewton meter, and the nominal capacity is 1450 kilonewton meter. With no LTB, the capacity of the section increases dramatically, and here we have the case where CB, the coefficient of bracing for lateral torsional buckling, equals to 1. So here we can see the capacity and the demand for the moment, the major moment, which is driving my design here. For sure, we can compare the properties for both sections, and you will see that all the properties for both sections are identical. Now for the other section, you can see that the properties are identical here, and the moment also is the same. The demand moment, major moment, 3,447 kilonewton meter. However, the capacity is 3,722 kilonewton meter. So what's the difference here? Why Etabs is calculating the capacity in a different way for the general section and for the predefined I section in Etabs? First of all, for general section, Etabs does not calculate the lateral torsional buckling capacity. So it considers the section with no LTB effect. So you can see here the moment, the nominal moment, equals to the nominal moment with no LTB. So always it considers the design for the section without lateral torsional buckling check. And this is dangerous and can lead to unsafe design in many cases unless you do a separate check, manual check, and confirm that the LTB is not governing or the load with the LTB limit state is still safe. So this is the first issue when using a general section. It does not design the section for lateral torsional buckling, and this is a big concern when using the general section in Etabs. For the other section, the predefined I section, it's 4,196. So it's bigger than the capacity for the general section without the LTP. Why? Because here for the predefined I section, the ETABS calculates the plastic capacity and it checks the elastic and the plastic capacity and it calculates the actual capacity based on the code limitations, the local buckling of the flange and the web, and it confirms here that my section capacity, the plastic capacity of the section, you can see it here. If you multiply this number by zero point 0.9 by the yield strength, you will get that the capacity of the section, the plastic capacity or the yielding of the section will be 4,196. So this is the governing, let's say, the governing capacity of the section if we don't have lateral torsional buckling. However, when we have a general section, it always check the elastic capacity. It considers that the section is unknown because we are defining it through this section designer. So it always uses the elastic section capacity, not the plastic or the yielding section capacity. So here you can see it uses S33 multiplied by zero point 0.9 multiplied by yield strength, which is the S355. the 355 megapascal. So we have two issues. First of all, the general section or the section designer, it does not calculate or check the member against lateral torsional buckling, and it always uses the elastic section capacity, not the plastic section capacity. So we must be careful when dealing with the general section.